Hello, ladies and gentlemen. I'm Mr. G, and today we're going to be learning about mapping Earth. What you need to have is, what this goes along with is a guided notes packet. I have it as number 30. It says topographic maps. You need that. You'll fill it along as you go. If you need to pause the video to fill in the information on the lines or label diagrams, you need to do that. So have your finger on the pause button as we go. So here we go, mapping Earth. So at a basic level, paper maps of Earth. Before there were phones and GPS and iPads, we had paper maps of Earth. And as a matter of fact, they are still very useful because a phone is only this little small thing. You can only see so much. You're zooming in and zooming out. But you have a big paper map that takes up a whole entire table. You can see a large section of Earth, and different maps have different show different features of Earth on them, and that's what we're really going to look at now. So for instance, on a phone or on a Google Maps or something, it kind of just shows roads and businesses, things like that. But we are looking at maps that include features of the land, like the hills and the slopes and things like that, that are not so much man-made features, but more the natural features. So you'll get a sense as we go. So here is a typical sort of topographic map as you see. I don't know if you can see the different colors in here. A lot of green on there that represents sort of vegetation. Think of forest or wood. So let me just zoom in so maybe you can see it a little bit better. So for instance, what this is showing is, it's probably a little light green right there. And this is called Flatiron Mountain, wherever this is. And it has these brown lines, and they have these interesting looking circular lines, and that shows elevation, how high it is, how high the land is. And they compare it to sea level, the level of the ocean, because that's very consistent. So for instance, this line right here is 4,200 feet above sea level. This is all going downhill, so that's 3,200. So this is going downhill, and then this is going to the top of the mountain. This represents sort of the top of the mountain, the round circle. And we're going to get into some features of this, but this is what I mean by a topographic map. These lines are called contour lines or ISO lines. So let's keep going with this. So some basic things, not a huge amount of definitions, but pause this and copy this down now, please. Okay, if those are contour lines, the contour intervals are what the lines count by. Okay, what each one of those brown lines count by, and it varies. Different maps are different. Have different contour intervals. So for instance, this map here, I hope you can see this down here, this is actually in meters. So whether it's in feet or meters matter. Mostly in the US, we're going to see it in feet, but sometimes they give you meters. It says 50 meters. So each line counts by 50 meters. So that's 500 meters above sea level. And they go, a meter is about 3 feet, a meter is about this long. That doesn't matter so much for this. But so where can we really see that? So for instance, that's 250 meters above sea level, and then that's 500. So each one counts by 50. So it's 250, 300, 350, 400, 450, 500, and then this line would be 550 meters. That'd be 600 meters. So also notice that usually every fifth line is darker and usually labeled somewhere. That really helps, or else it'd just be a weird jumble of lines. So the darker lines help us as well. So for instance, this is a real map, and real, we call it USGS topographic maps in the United States, they will always say, they have a very consistent format. It will say contour interval, in this case is 10 feet. Each line on that map counts by 10 feet. Always start with a map by looking at what the contour interval is, because it does vary between different maps. Please copy this stuff down now, pause it. Okay, a benchmark is a specific location where we measured the exact elevation, usually years ago. It shows the exact elevation of a specific spot, often to the individual foot. So for instance, this is an example. If you see on a map, BM means benchmark 324. That means the elevation is exactly 324 feet in that spot. Now, what does that look like? On a map itself, this is a real map of an area in upstate New York. This intersection here, it has BM, it has an X, so right there, BMX says 304. So that's 304 feet above sea level. And you'll be able to go, what they do, the people who measure this, they will actually put a metal disc in the ground, and they cement it into the ground, and they will mark 304 feet on there. so that people can measure to that. And then if you're 10 feet above it, you're 314 feet above sea level, for instance. That's why they do it. So it looks like this. There are these like brass or bronze discs. This one says 103 feet, and they're about this big. And just to give you a sense of scale, that is me in my bearded days taking a picture with a benchmark marker right there. See, it's gotten a little green over time, but it's about this big, and it is cemented, and you want to put it somewhere where it's not going to change. You don't want to put it in a tree, and then the tree grows or falls down. So it's usually like cemented into solid rock somewhere. That's a benchmark. Okay, next up, I have this. We have this. Please copy this down for gradient. So gradient is a term that we use for a lot of different variables in science, but let's just focus on maps for now. For maps, by gradient, it means slope of the land. High gradient means steep slope, and low gradient means gradual slope. So for instance, if this is a profile of a mountain here, right, between the two red lines, right, we have the pretty high gradient. It's pretty steep right here. So between the red, but yet between the two blue lines right here, it's much flatter, more gradual. So it's a lower gradient, more gradual slope is what we say. And we want to measure these with numbers. I always say, in the world of science, we want to quantify things, quantify, and think of what word is in quantify. Quantity, put a number on it, right? That's what we do in science. We want to get data, we want to measure variables in science, put numbers on them so we can compare them. That's why if you go outside and there's the weather, you say, what's the temperature? You don't say hot or cold or cool. We really want to get into a number, and we use Fahrenheit and Celsius, and it is 74 degrees or it's 32 degrees, something like that. So that's what gradient does. It's going to give us a number for how much the slope of the land changes. Next up is profile. So please copy that down. And a profile is a side view. So what we were just looking at here, this right here is the profile of this mountain side view of it. We'll be drawing those, actually. You'll be drawing those, which actually is pretty cool. Students usually like it. So let's keep going. So for instance, please pause it and copy these two words down. So we're doing two things here. We're looking at two things. So we're looking at a profile view of a mountain, and then the map view. So this is showing the isoline view. So for instance, I really like this to help, right? Notice how steep the slope is here, and it's much more gradual here. So if you drew these lines 100 feet, 200, the contour interval here would be 100 feet. You drew these lines here, and you drew a line where everywhere on the line is 200 feet above sea level. It would look like this line right here. That's what this line is. Okay, so this is the topographic map view, and this is the profile view. We will be taking a map view, and you will be able to use a pencil and a scrap paper and draw this, which is cool. But one key thing, where the slope is steepest, notice the contour lines are really close together, and where more gradual slope, they're further apart. That is key. Make sure you know it. Okay, some rules of contour lines. So you'll be drawing these, we call them isolines, because they can be used for a lot of different variables, a lot of weather variables, temperature and air pressure, and depths of lakes, things like that. But for us, for maps, when we talk about elevation, we tend to call them contour lines. So some of the rules are contour lines can never touch or cross each other. I'll get to that in a second. And lines are either closed circles or run off the map. They can never just end. Okay? You never just end, and that's something you learn as you're drawing them. So here's an example of what I'm saying. So let's say this is the 450 feet contour line right here, and this is the 400 feet. Well, so this is breaking the rule. You cannot do this because here they cross. Because what can't happen is that can't be both 450 feet above sea level and 400 feet. We can't be. If you ask a kid in class, how old are you? You can't say, I'm 14 years old and 16 years old. Can't be, right? You can't weigh 152 pounds and 177 pounds at the same time. Can't be. So they cannot do this. They can't cross. They can get really close to each other when it's really steep, but they can't touch or cross. So another rule here is the closer the lines, the steeper the slope of the land. So please pause this and write this stuff in. Right, so what you're seeing here, this is a mountain, this is a more gradual slope because they're further apart. This is the steeper slope of this little, maybe it's probably more of a hill, it's only 75 feet above sea level. See, contra interval is 5 feet. So that's interesting here, and we need to know that because here's a question that we have on here. Let me dismiss that. A possible elevation of point X. What is a possible elevation of point X? So see if you can do that now. If you can't, wait and I'll show it to you. Okay, hopefully you got an answer for that. So if this is 50 feet and 75, they count by 5, right? So 50, 55, 60, 65, 70, 75. So I got to figure out where this is. This is here. This is the 50 goes around. So 50, that line is 60, that line's 65. Well, that's in between. So it's not on the 55 or it's not on the 60. So you can't say 55, can't say 60, or else the dot would be on one of those lines. It has to be between those. So any of these answers would work. And this is kind of, so any of these, if you see what I wrote in here, 56 feet, 57, 58, or 59. If you wrote one of those, you got it correct. Good job. If you didn't, hopefully you can see why it is any of those 4 answers. Okay, let's keep going. Here we go. Stream flow. So this is another rule of contour lines. Stream flow. When contour lines cross the stream, they form a V, and the V points uphill. Please pause it and copy that down now. The V's point uphill, so the pointy part of the V points uphill. This tends to drive kids crazy, a little bit, but you will get this, don't worry. So in this case, you have Fish Creek, and I show the flow direction. It is flowing out of the lake. And then what I did is when any sort of river or stream crosses contour lines, it forms a V, and the V points uphill, right? The kids really want the pointing to point the direction it goes. It'd be so easy, right? Like an arrow. It'd be so easy, but it's actually the opposite. And this is because rivers, as they flow over many, many years, they carve and they erode a valley, and just by the nature of how contour lines work, the V ends up pointing upstream. So oftentimes we want to know what direction the stream flows. Stream flows this way, V's point uphill. So in this case, Fish Creek flows towards the east. If this is north, south, east, and west, what direction does it flow? Let's do another example. Okay, Mud Creek flows toward what direction? So what they gave in this diagram here was a question. They gave just a north arrow. Now, what you need to know is, and they expect you to know, so I want you to learn it now. In our compass rose, that way is north, that way is south, east is that way, west is that way. And almost all the maps that we'll see, actually pretty much every map we'll see in school is oriented this way. So north is that way, south is that way, east and west. So in this case, Mud Creek is right here. This is the ocean. So let's see. Right, look at the V's here. The creek is flowing that way. The V's point uphill, so it has to be flowing the opposite direction. Therefore, Mud Creek flows towards the southeast. Please pause this and copy that stuff down now. Okay, another part of contour maps that they have to deal with once in a while, not that common, is what happens if you have, we're used to having a top of a hill go like this. What if you have like a bowl shape? The land makes a bowl shape. How are you gonna show that? And it's a little challenging. Not that much of a big deal us in the Northeast where we live, because usually if there's a bowl-shaped land, it has filled up with water. It's a lake or a pond, but it happens sometimes. And so they want to show these circles here are not the top of a mountain, but instead they're a depression. The land goes down again like a bowl shape. They show these little like hair-like lines in there. So for instance, and I like how this is drawn, you see this here, how it kind of goes up and it has this like depression in there, this bowl like it goes down. So how they show it here is this is 290 line right there. So then this is showing, it's going up 280, 290, 300. Then it's going back down. So it's showing part of the hole. So it has these little hash marks in there, the little lines, 300 and 200 showing in there. So be aware of that. Do some mapping practice and you'll be able to put this to use. So what we're going to do here, we're back to this same little hill here, steeper here, more gradual here, and then we're going to calculate gradient because, like I said before, we want to quantify things in science. We don't want to say, oh, that mountain's really steep. It's kind of steep. It's flat-ish. We don't want to say that. We want numbers to compare to. Science is always quantifying things. So in this case, contour interval is 5 feet, elevation is feet, and then this is showing distance, and you would use this piece of scrap paper in order to show that. Now that's a little challenging for me to do on this board because it acts all weird, so I'm going to do my best. Please pause it and copy this down. Okay, gradient, like I said before, for contour maps is how steep the land is. Now there is a formula. It is on the Earth Science Reference Table. It is the change in field value divided by distance. A lot of kids don't like that. What's a field value? Why aren't we more clear? It's a pretty broad gradient formula that we can use for a lot of different variables, but the field value is whatever you're measuring. On maps, we're measuring elevation. And the distance is this scale. So the elevation is this, and the distance is sort of this way. So we'll get a sense by doing this. So for instance, if I drew this side of a hill here, A to B, the change in field value is going to be elevation. Well, B is at 200 and A is at 500. So 500 minus 200, 500 minus 200 is 300 feet would be the change in field value here. 500 minus 300 feet change in field value. And then the distance between them is this way. I have it here. So the distance would be this. Okay, and the only way you really can measure that is if you have some sort of scale down here to hold a piece of paper up to mark it, which we have on our examples. So I just wanted to show that. So here we go. Look at the first one here. Calculate the gradient between A and D. Where's A is here and D is there. So what I usually encourage people to do, this is the front page of the Earth Science Reference Table. The gradient formula is here. It's given to you. You don't have to memorize that, which is nice. Change in field value divided by distance, and usually write that down to help you with that. Write that down. That really helps. The kids who don't do it tend to make simple mistakes. Change in field value divided by distance. So A, if they count by 5 feet, A is that's 50, 55. A is at 60 feet, and then that's 60, 65. D is at 70 feet. So it's 70 feet minus 60 feet, and then and I'll show you that in a second. To get the distance, I won't be able to do that. What you do is you will hold your paper up to the page like this. Ooh, see? It goes crazy. Man. It goes crazy. You hold your paper up to here and you mark A and you mark D, and then you hold it up to your scale right there, and then you measure how far it is. If that's 1 mile, so that's 0.1, 0.2, 0.3, 0.4, 0.5 miles. You do that. You really need to get practice on paper doing this. Hard for me to do on this board, as you saw the thing just freak out. So what we have here, the change in field value is 70 feet minus 60 feet, 10 feet. The distance is, you should have gotten 0.2 miles, right? So then you do 10 on a calculator. You type in 10, hit divided by 0.2, and hit equals, and then you will get 50 feet per mile. So what that means is if you're going this way, you're going uphill, for every mile you travel this direction, your elevation is rising by 50 feet. So we're putting a number on the gradient. Let's do another one. Number 2 says calculate the gradient between C and E. C is there, E is there. Change in field value, well, E is right on the 50 line. And you can do it like this actually. 50, you want to count by 5s. So then you can just do 5, 10, 15 if you can count by 5s. So it's 15 feet is the change in field value. Right, so that's 60, and you can do it this way too, 65 minus 50, 15 feet, and then the distance, if you put a piece of paper up there and you mark that and mark that, hold it here, it's 0.8 miles, and then what you get is 15 feet, so in the calculator, 15 divided by sign, 0.8, you hit equals, and you will get 18.8 feet per mile. and I rounded that to 1 decimal, to the nearest tenth, 1 decimal place. But, and that means again, so now this is not as steep. Every mile you travel this direction, you will then change elevation 18.8 feet, about 19 feet. Number 3 looks like this. So number 3, B and F. So the change in field value, again, you can just do it 5, 10, 15, 20, or I did it this way, another way to do it, 65 minus 45, 20 feet. And this distance is 1.4 miles. So 20 feet divided by 1.4 miles, you get about 14.3 feet per mile when that's rounded to the nearest tenth. Hope this is making sense. There is one more remaining. And it goes like this. So what do we got? What is this? G and H. So G and H here, the change in field is 15 feet, but they're not that far apart, 0.4 miles, 37.5 feet per mile. And the real reason you want this is if you're hiking, or oftentimes if it's a road and you're driving a vehicle, how steep is the road? How steep is this hiking trail? Because if you're hiking and you're carrying a big pack, you want to get a sense of how steep that is. And if you're driving a vehicle and maybe you're towing some sort of trailer, or your vehicle is really large, can it make it up that grade is the word that they would use. So one of the uses of gradient